of us going to be there at the same time, or?
Yeah, we're live
Okay.
right now. We're still recording. So welcome everybody to the first ever test pilot episode of Science Unplugged on the web. The purpose of this is to give the public access to scientists like you see before you on your camera right now. And the goal is that we're going to have a guest appear every time we do an episode of this who specializes in a different field. They're going to give us a synopsis of their work in a way that is easy for you to understand, to get you excited and interested in the world of science, and to hopefully inform you and let you know that science is a very broad area of study, and that there aren't people just doing biology and chemistry, but there are people who are studying things that are at the farthest reaches and edges of our universe. Isn't that right, Steven?
Yes, it is.
Okay, great. So my wonderful guest tonight is my good friend, Steven Jaret, who is a PhD candidate at Stony Brook University. He is in the geosciences department. And I guess the best way to describe your passion for science is that you love rocks.
That is correct.
Okay. So, Steven, why don't you give us a little bit of insight into what it is that you do in your department, what it is that you're researching, and tell us about your scientific passion.
All right. So I'm a geologist. And the area that I study is I do what's called planetary geology. So I'm interested in the rocks both on Earth and any rocky planet out there. And I use the term planet to mean, very vague, very general to mean anything that's orbiting the sun that's rocky. So what I study is a process that's common across all of these planets, and that's what happens when meteorites or asteroids slam into the surface of planets. So what I do is I go around the Earth to examples of craters here on the Earth where an asteroid has landed. Most of them happened millions and millions of years ago. But you can look at the rocks and try and understand what happens to the existing rocks on Earth when they get slammed into. And the reason I do this is to then think about how to understand the other planets where this process is really, really common. And so the samples we have from other planets, rocks that the astronauts brought back from the moon, and meteorites we have, they all have been involved in these similar asteroid collisions. And so I want to understand that process so I can understand the other bodies.
Very cool, very cool. So let's take a big step back, and I just want to know more about the environment that you work in. So, I'm a microbiologist. I work in a lab. I have centrifuges and test tubes around me and petri dishes and stuff. What does your research environment look like? Where do you do your work?
So I actually do my work in two different places. The first place that I do my work is outside in the field. Part of the reason I love being a geologist is I get paid to go hike around mountains, and usually involves carrying a giant sledgehammer, going and breaking off pieces of the rock, and making measurements and looking at them in the field, then bring them back to the lab and do other kinds of lab studies on them here. But mainly, first thing you do is you go out in the field, which sometimes actually is a giant field. I've been out in cornfields and cow pastures and, mountains.
What's the most exotic place you've gone to look for space rocks?
So during my master's, I worked in an area, it's impact crater in Norway, which was pretty sweet. It's about 3 hours north of Oslo. And so you just drive in and drive out in the country, and then you're hiking through the Norwegian wilderness. It was pretty awesome.
Actually, I don't think I did this. Can we talk about what about your educational background? So where did you do your undergrad? You did a master's before you started your PhD. So
yes. I have a long and circuitous academic path, but my undergrad started at University of Tennessee. I'm originally from Atlanta, so I got my initial training at a science center down in Atlanta. Worked in a planetarium there and an observatory, and got really interested in space, and there was a meteorite collection there. Then I went to University of Tennessee because they have a really good program for people who want to study meteorites and planets. Then I did my master's at Harvard, and then arrived back here, Stony Brook.
Very nice, very nice. So let's get some of the terminology right. What's the difference between an asteroid?
So I was just going to say, I noticed that someone on the side was commenting about Pluto. Okay, so there's a big controversy, right, of what is a planet? And I take the geologist approach that, to me, planet, I'm concerned about the rocks, right? So any body out there that has a rocky surface, I consider that a planet. You know, if it's the moon, if it's an asteroid, if it has rocks, I care about it. To me, the Earth is a lot more similar to Pluto than it is to, say, Jupiter, which is mostly gas and not solid. So there are these formal definitions of planets, and to some extent, how you classify things is dependent on what your point is. So if you're like me and you care about the rocks, I consider all the rocky planets planets. If you're a physicist and you want to understand about how the motions of the planets work and how they revolve around the sun, then maybe you would define things based on different. But to me, Pluto, I think Pluto is a planet, yes.
Somebody put a comment, Jupiter is not a planet to geologists. Because
well, it's not. It's a failed star.
That's great. So let's get some of the terminology right. What's the difference between an asteroid, a meteor, a meteorite, comet? There's a lot of
there are a lot of terms. Yeah. So the big difference between comet and asteroid, this is one that's actually based on what it's made out of. So, and a little bit, to a little extent, where it is in the solar system. But the main composition difference is asteroids are mostly rock. Comets are, we kind of think of them as light and fluffy. The best example I've heard of is they call it a dirty snowball, where it's mostly ice with some rock in there too. And comets also have a different spot in the solar system. They start out in very far edges of the solar system and occasionally get brought in an orbit, and depending on the circumstances, they can come around multiple times, like Halley's Comet, or they can come once and just be done. Asteroids stick mostly in the inner solar system between Mars and Jupiter until they come flying into the inner solar system. So those are the big, what it's made out of determines whether it's a comet or an asteroid. Then if it's rocky, we get another bunch of terms based on its size. So if it's big, we call it an asteroid. If it's medium-sized, or like this point we're talking like head size or basketball size, then we call it a meteoroid. The term oid just means kind of like, so it's kind of like a meteor. And that's if it's out in outer space. When it enters the Earth's atmosphere, we give it a new name, and that's a meteor. That's what you see as shooting stars flying through the sky. They're not actually stars. They're mostly small pieces of rock and dust. And then if it hits the ground, you give it a new name because geologists like naming things. And so we call it a meteorite. So out in space, meteoroid. In the atmosphere, meteor. On the surface, meteorite.
Awesome. Now you actually segued very well into the next thing I want to ask you, is that a lot of this.
Take a moment and apologize to the people on the side who their questions pop. I'm still getting used to what this looks like.
Oh yeah, we're gonna.
I see some questions, so I'm not ignoring you.
We're gonna tackle them in a little bit until we're gonna dive some more into your work, and then I can actually have the questions appear on the screen for everybody to see as well. So, and then we'll open up the camera as well for other people to jump in. I
apologize. There are like lots of things flashing around that I'm like, what is going on?
Don't worry. Welcome to the interwebs. So, and also for our viewers too, if you like what you see and you want us to continue doing this some more, please feel free to share, tell a bird, tell your friends on Facebook. You can do that on the side here. We want to see if we can really make this one of the most intriguing, interesting, and popular shows on Blab, at least for tonight and hopefully for the future. So Steven, you mentioned that a lot of this material, once it crosses the atmosphere of Earth, it's now called a meteorite, and that we, throughout the history of our planet, have been bombarded quite a bit by these rocks. How much of this material actually has landed on Earth? How much does it happen every day?
So some of that depends on how big. So if you actually want to know how much stuff from outer space hits the Earth every day, the number I think it's 60 tons of material per day, which now granted most of that is like dust size or smaller. So we're not getting hit with a 60-ton thing. I hope that's the right value.
Either way, it sounds like a lot.
Close. It's in that ballpark. But most of that is just fine-grained dust that just rains down, and you don't even notice. the bigger things happen. So something, these are big impacts happen less frequently than small things. So like the dinosaur killing event, which was huge, by the way, it left a crater close to 100 miles in diameter wide when it struck. Those happen a lot less frequently than something small. And by less frequently, I'm going to do something I probably should not do and pull up. I want to make sure I get this value correct.
That's good. We want to make sure our viewers are getting the actual statistics live in person.
I don't want to rely on my brain at 8-something p.m. I apologize while I look this value up.
But that's amazing that tons of material are bombarding Earth every day from outer space. I don't think that's something that we have, a concept of, most of us, right? We just walk around and we don't really think about that much.
Yeah, and the cool thing about the dust is that comes down at a fairly constant rate. So one of the things actually that was done way back in the 80s, they were trying to figure out, how long it takes for rocks to get laid down. Like what you see a lot of times are sediment that just gets deposited in the ocean. Eventually, all rocks eventually break down and travel down rivers and streams, and ultimately get into the ocean where they're just laid down as sediment. And one of the ways they tried to figure out how long that takes is to measure the amount of this cosmic dust, because that's a constant amount. And let me see what we do here. It's unplugged.
So it's raining space dust on us all the time, essentially.
Yeah. Yes, it is, which is a little terrifying.
I wonder if we
really
could sell space dust umbrellas. I wonder if anybody would purchase that.
I found this reference. Let me pull this up.
Oh, somebody here in the chat said that 214 tons per day, according to Cornell.edu.
That sounds about right. I imagine that this is a fairly hard value to actually calculate. Okay, so these are some statistics of how frequently things happen. So if you have a rock 2 meters, and I apologize, this is all going to be in metric, something that is 2 meters wide hits the Earth about every 4 years. Wow, that seems really frequent. Something that is something that is 500 meters. So this is big. That happens every 100,000 years. Something that would have taken out the dinosaurs happens once every 26 million years.
I see.
And that's kind of scary, because the dinosaur, that was 65 million years ago. So, we're due. That's what you want to hear.
Well, you're proving to us that you are the modern day Bruce Willis, and that you.
That's one of my favorite movies, by the way.
It's an Armageddon reference for those of you who don't know what I'm talking about. But that's kind of true. Is that Hollywood depicts science in a certain way, but you're the guy that we're really going to turn to in the end when it hits the fan, I guess, for another way to say
I
it.
apologize in advance, everybody.
There you go. So we'll take one of the questions that somebody put up. So how can you tell a space rock from a mundane earthly rock? And can you see that? Can you see all the...
Yeah, I can see the question.
Okay, cool.
That's actually a really good question. And this is one of the other fun things that I like about what I do is since I study these kind of rocks, a lot of people come into the geology department and they say, oh, I have this really weird rock, or it looks weird. Is it a meteorite? Or a lot of families have stories that, this thing Grandpa saw fall out of the sky. And They bring it, and that's what I get to do, is identify it and try and tell them, yes or no, and how you can tell. And so there are a couple ways you can tell. One, some of this is not all that satisfying to someone who's wanting to know. Some of it you can just look at it, and as an experienced geologist, looking at it, you can tell they have a particular kind of texture. Some of the things you look for is whether or not it's magnetic. So that's always the first thing I ask people is it magnetic? Now, not every rock that's magnetic is from space, and not every meteorite is magnetic. But the thing about meteorites is they contain a lot of nickel and iron that you don't normally find at the surface on the Earth. When the planets are forming, there's this process where you take all of the nickel and iron and it got brought down to the core of the Earth. This is a process called differentiation, where you start out with some big ball of all of the elements mixed together, the iron, the nickel, it all gets pulled down to the core.
Is that
now in meteorites?
Is that because of magnetism, or how does it?
It's basically it's density driven.
Okay.
This is back when the planet is cooling, it's solidifying. It's not solid yet, and that dense metal falls down to the core as the planet's cooling. And this happens. There's a size that this, in order to do this process, you have to be a planet that's big enough. And a lot of the meteorites start out as small objects, smaller than, it's going to be big still to a normal scale, but we're talking, things that are smaller than the moon. They don't actually go through the process of separating. So you get a lot of this iron and nickel together. So when you see a rock on the surface that has a lot of iron and nickel in it, one way to get it up to the surface is it's a lot easier to get it down from space than try to get it up back out of the core.
I'm really I'm very interested. I mean, this idea of how do you tell an Earth rock from a space rock? When you go out into the field, what are there? So I know there are two classifications, finds and falls, of identifying these rocks. Can you tell us about those?
Yeah, so we call a find a meteorite that someone found on the ground, and they picked it up and brought it in. We identified it as being from outer space. Usually you do a nickel test. There are some other ways you can look for it. Sometimes you can look at oxygen and some of the other elements too. But the other way you do it is what's called a fall, where someone saw a meteor in the sky and actually saw it land and picked it up almost immediately. Those are a lot less common. A lot of times, lots of people see the object, and it's real easy to think that, oh, it went down just over that other hill over there. But most of the time, they're really much further away than you think. So actually finding it immediately and witnessing a fall is a lot less common than just picking something up.
Wasn't there one that was on video that was actually landed in Ohio, but you could see it in Peekskill, New York?
Yeah. So there's some really good video. They do get captured a lot. And I have friends who are airline pilots who tell me that they see a lot of meteors.
Oh, that's very reassuring.
I don't know of any plane that's ever been struck, though. And there are a lot of planes flying around, so the odds are pretty good. I mean, good that it's good that there have not been any that have been struck. So the one in Ohio, this is a famous meteorite called Peekskill. It was seen all over the East Coast, and it ultimately landed in Peekskill, New York. And when it landed, it came crashing down through the back end of a car. And the car was on museum for a while, on display for a long time.
There is a story that I know of a woman who...
yes, Mrs. Hodges in Sylacauga, Alabama, who... I think it was 1954. And she was lying in bed, and a meteorite came crashing down through the roof, bounced around a little, and then struck her. And she survived. So this is the only person to have ever been struck by a meteorite. And she lived. She had a giant bruise on her side. I mean, this was like serious black and blue mark. Well, the funny thing was, okay, so what do you do with it, right? Because she was renting the property. And the landowner claimed, well, it landed on his property, so it was his. And she claimed it landed on her, so it was really hers. And there was a big dispute, and ultimately it got donated to a museum or university in Alabama. And actually, I went back and I was living in Alabama for a while, and we visited the house. This was 2004, we went down there, and the house was still there, and the hole in the roof was still there.
That's pretty awesome.
Like 50 years later.
So, I mean, there are more recent events in meteor history, right? A couple of years ago, there was an episode over Russia, right? And this was very well recorded. So what happened with that? Why was that such a big deal?
Well, that was a huge deal because it was daytime. And so a lot of meteors are bright when you see them at night because it's bright against the background of dark sky. This one was particularly bright, so bright that it was seen during the day, and actually it was almost as bright as the moon or brighter in the sky. And it was loud. It actually the explosion took out windows in the town. Like everything was just blown apart. And it was captured on video because in this part of Russia, everyone drives around with a dashboard camera to protect themselves from corrupt police.
Wonderful.
And so everyone was driving around, and so all of the cameras caught it, and you had so many different angles. It actually helped in backtracking the trajectory of it because they used some of these camera angles to figure out where it went.
Some people are asking on the side, what about Tunguska?
Yeah, Tunguska was also a really big event. That happened in the early 1900s. And what's interesting about Tunguska is it didn't actually hit the ground. It was an object, probably a comet. We don't really know. Ooh, something happened here.
I X'd out the question.
Oh. So it exploded in the air before hitting the ground. Probably the reason we think it was a comet is because comets have a lot of ice and other gases in it. And so those heat up and it exploded and broke apart before hitting the ground. And even that was enough to take down a forest in Siberia. So the explosion of that, though, was nothing compared to what would have happened if it actually hit the ground. It would have been even much worse. But
how much worse?
Lucky because it exploded before it hit the ground.
How much worse are we talking here?
Well, so it exploded in the air, and we don't have an actual crater. One of the problems with Tunguska is there's actually no crater there because it took down a forest and blew out a bunch of blew down trees, but it wasn't even big enough to make a hole. So if it had hit the actual ground, and it's hard to know how big it would have been because we don't have it, so we don't know how big it was. But there would have been a substantial several mile wide crater.
So you go to crater sites often. So I mean, in the United States, there's a crater in Arizona, I believe, or
yeah.
It was in Arizona. And can you tell us how you study those craters and the impact, and what can you learn from going to those sites? And that's a pretty big crater, from what I understand. I've never seen it.
So it is a large crater. It's about a mile in diameter, which sounds big, but compared to craters on the Earth, that's actually in the small category. It's considered among craters, it's kind of a small one. And what you can see is you can actually look at the rocks, and one of the things that happens is rocks that are in the bowl of the crater get thrown out onto the side, and we call this ejecta. And so one of the things that we look at is what the pattern of the material coming out is, and all of that material in the crater has to go somewhere, particularly thinking about how it affects the environment. It's a lot of pulverized rock and dust that gets thrown up and out, and a lot of that goes into the atmosphere. And so one thing you have to wonder about is, where does that rock go? What does it do to the surrounding environment? Obviously, if the sky gets covered in lots and lots of particles of dust, it's going to block out sunlight. It's going to dramatically change the environment. The other thing that you can look at is what happens to the actual rocks that stay in the crater. One of the things that I am interested in is what happens to those rocks? Do they melt or not? Sometimes it's so much energy that you actually melt the rocks, which can be useful for then going back and trying to figure out how old it was or when it happened. Because if you have these rocks that get melted, they'll create new rocks. And so then you can use those new rocks to learn when the impact happened.
Very cool. So I'm going to take some more questions here from the side. How much of Earth's oceans can be attributed to impacts from meteors, comets, etc.?
That is a really good question. And this is a big debate and a big question for the Earth is, where did Earth's water come from? This is one of the things that separates Earth from most of the other planets. And all of the other planets, there's some of the moons of Jupiter may have oceans. But a big question is, where does this water come from? And there are two possibilities. One is this water came from comets, because they're mostly ice. So you deliver the water from outside the Earth by throwing comets down. The other possibility is that the water came out from the Earth. As the Earth is cooling, it started out as this molten ball of everything. And some of that water got sequestered in, and as volcanic eruptions are happening, that water is coming up out of the Earth. So it's this big debate of, where did the water come from? So you could do it purely with comets. You could do it purely with volcanoes coming out from the inside. Or you could do it with some combination of both. Now, the actual question of how much, do you mean how much comet would it take to form the Earth's ocean? Or do you mean how much of the current ocean could be from a comet?
That's a good question. We'll have to wait for him to ask that again. But getting back to this topic of that meteors and asteroids and comets can contain water within them, somebody asked here on the side, Doug asks, can life be found inside a meteorite? And it'd be interesting to get your perspective, because this is what you study. You study these rocks. So could you have life inside?
Yeah, that's an interesting question. And I assume that what you're referring to was the big story back in the 90s, I think 96 or something, where there was a meteorite that originated on Mars. And there was a big report that came out where they found these things that look like little bacteria. That has mostly been shown now to not actually be life. Most of the reports that have come as follow-ups to that study, most people would say now that those are not actual bacteria or life. And it's the case of a lot of times, particularly when dealing with microscope work, a lot of things can have similar shapes and similar sizes. So I'm of the opinion that Martian meteorite doesn't contain life. Now, does that mean that we will never find life in a meteorite? I think it's probably unlikely, but I don't know for sure that I can say you couldn't get it.
What about other organic compounds? I believe they found sugars and
yeah,
alcohol.
they've definitely found sugars. There's this one, some of the meteorite, I can't remember which meteorite, but they call it the sweet meteorite. They say that it has a sort of sweet smell to it. They've found sugars and they've found amino acids. And so I guess that depends on what you consider an organic. I see someone say organic at all. Yeah, so are amino acids organic? That'd be a question for the chemist, Peter.
Yeah, amino acids they're carbon based, so they're organic compounds. They're part of the biochemistry. So, somebody, Adam here asks, is Jupiter entirely gas, or is there some solid core down there in the middle?
Ooh, that's also another really good question. Well, so we've never actually been to the core of Jupiter. So I'll clarify it with that. We think there probably is a rocky core somewhere down at depth. Exactly what it's made of, what kind of solid it is, probably iron. We don't really know. The way we do these kind of measurements is when you fly spacecraft around the planet, you can measure things like its inertia and its moment of inertia, and you can get good density measurements. So we think based on that, there probably is some solid core at the center of Jupiter somewhere.
Very cool. So I have a question. So we mentioned Martian rocks on Earth. So there is an exchange of material that goes on between planets?
Yeah, so this is, I think, the coolest part. So we actually have meteorites that landed on Earth that we can trace back to at least two planetary bodies for sure. There are some that we can say for sure started out on the moon. There's some that we can say started out on Mars. There's another set that we can say to 99% certainty which asteroid it started out on. But the basic idea here is there's some other planet, say Mars, sitting there orbiting the sun, and just like big asteroids hit Earth, big asteroids hit Mars. And Mars has slightly thinner atmosphere, actually a lot thinner atmosphere, and less gravity. So it's easy to get these pieces of ejecta that go flying up after the impact. They can get launched out into outer space. And so now these Martian rocks are just floating around the solar system doing their thing, and something causes their orbit to change, and they go in toward the sun, close to Earth. And then Earth happens to be approaching at the same time. The gravitational pull of the Earth pulls in these rocks that started out on Mars. And they make it in. They go through the atmosphere, come all the way down, land. We found them. Because, 3/4 of the planet is underwater. So the likelihood of it landing somewhere solid, somewhere where we actually then found it, then we figured out that it's from Mars. I mean, that's a really cool rock.
Somebody asked, how do you know where they're from?
So we know that they're from, if it's the lunar ones that come from the moon, we actually have samples of the moon that Apollo astronauts brought back. The only other body in the solar system where we went with people, got samples, and brought them back. So we know what those look like. For Mars, we've sent spacecraft to Mars. And one of the things that Viking did was measure the atmosphere on Mars. So when rocks, particularly volcanic rocks, when they erupt on the surface, they trap some of that atmosphere in them. You go to Hawaii and you look at the rocks, and they have atmosphere trapped, gas bubbles trapped in them. So we got these rocks, these meteorites, that started out on Mars, and they have gas bubbles in them. And we measured that gas, and it doesn't look like Earth atmosphere. It looks like Mars atmosphere.
That's awesome. Is it possible that we have rocks or on our surface that are from planets that are a part of other solar systems, maybe other galaxies? I mean, how far out can we go,
So that's a really interesting question. Now this, I guess, gets to the question of how do you define planet, right? So there are these things in the meteorites that we call PreSolar grains. And these things are really, really, really tiny. But because of their chemistry and some of the elements in them, we know that they had to actually start out in a pre-solar system setting. So the solar system we're in right now doesn't go all the way back to the beginning of the universe. Our solar system is only about 4.5 billion years. And yeah, I realize I just said only 4.5 billion.
You're such an ageist, Steven.
Yeah. Well, I mean, okay, so when you compare it to the age of the universe, which is in the 14 billion year range, and Max is probably going to yell at me for estimating that value. But compared to the age of the solar system, it's significantly younger. So there were things that were existing pre our solar system that got incorporated in when our solar system formed. And they have these in some of the meteorites. And that's cool, because it's older than the sun.
That's crazy. Just for the record, we do have a cosmologist, another cosmologist in the room watching us as well. I don't know if he's still here or not, but and if you say anything wrong, he's going to correct you, maybe.
Please correct.
Peer review in the live peer review, maybe. To me, this sounds like a cosmic pinball game. essentially, right? It's just like things are flying out and then they're just looping around and you're getting caught in the track of another planet. And it's just, it's absolutely
It's really cool.
All right, so we're going to try, this is going to be the second segment of the show because we're going to go till 9 o'clock. I got 8:38 on my clock here. And we're going to open up the cams and let some of our viewers, we have 56 people watching us right now.
Oh, wow, 56 people.
We've had 182.
How many people care? I'm impressed.
That's right. We've had 183 people viewing us this entire time in total. So I'm going to open it up, and then I'm going to have to close you out quickly, though. I'm just going to ask you guys to ask your question. Maybe we can have a brief discussion, but I want to get as many people as possible in here who want to ask questions. So if I ask you out, no hard feelings. I just want to keep the thing going. So we'll open this up. And anyone is free to jump in and ask a question. In the meantime, if anyone doesn't ask a question, oh, here we go. Adam Hassan wants to come and ask a question. Let's see if we can get him to work. Sometimes it gets a little glitchy and cams don't load. It also depends on the person's Wi-Fi. Hi.
Can we do this like car talk where we ask you where you're from?
Sure. So Adam, introduce yourself, where you're from, and what's your question for the geologist, Steven?
Yeah, hi, Adam here. I'm from the wilds of northwest New Jersey, the part of the state that no one knows about a half hour from the Poconos in Pennsylvania. So I was the one who asked a question about Jupiter, but then I got really intrigued with the notion of, tracking matter from other planets landing on our planet. Is there any process by which matter from Earth goes out and ends up anywhere else?
That's a really good question. Probably. So there are probably Earth meteorites on the moon. There is the added complication of Earth has a very thick atmosphere.
Yeah.
So it's a lot harder to get something off Earth onto the moon.
Sure.
And Earth has a pretty strong gravitational force. But there are probably Earth meteorites on the moon. That people have suggested that.
Very cool.
We haven't found any, but good reason to go back to the moon.
There you are. Thanks so much.
Thanks
for listening.
This is great.
Going to close up the page. Hold on a second. Yes. Okay. There we go. Okay. That was great. So that worked perfectly. That's exactly how. Thank you, Adam, for being such a great example of how we want this questioning to work. So if anyone else wants to jump in with a question, in the meantime, we can also take some questions from the side here. Timothy West asks, can you escape a black hole like Eric did in George's Secret Key to the Universe?
I don't think so. One of the things about black holes, and I will clarify to start off that I am not a cosmologist, and so my knowledge of black holes is probably the same as yours. But
probably.
Black holes, to my understanding, is what makes them black, is that the gravitational force is so strong that not even light can escape. And light, of course, is the thing that moves faster than anything else in the universe. So if the fastest thing can't get out, I'm doubting you could either. If
Max is still here, he's more than welcome to jump in and tell us about the nature of black holes, since he's probably the expert on that. That's very cool. So this is a question from a while ago I never got to. What is the concentration of dust in space per meter squared to deliver that statistic?
Ooh, that is another fantastic question. I don't know the concentration of dust. I do know that they've measured this. One of the things that they measured this with was the spacecraft called Cassini, and also I think the one that's out near Pluto. But as these spacecraft, Cassini went to Saturn, and New Horizons is going now at Pluto. One of the things they did while they were traveling out to these outer planets was they had dust counters on them to see how many particles they encountered as they were traveling. And other than telling you to look for it in that sense, I don't know the concentration of dust.
Speaking about dust, so when the meteor struck the Earth that created the mass extinction of the dinosaurs, right? Some people may think in their head that this caused some
Thank you, Max. I see it now. Interstellar space dust is 1 gram per cubic centimeter.
Oh, there you go. That's
Thanks,
why we
Max.
need a cosmologist to help us with these quandaries. So some people may think that when the dinosaurs went extinct, a meteor hit the Earth, and that this like tidal wave of earth and rock and water just came and swept everything away, and that's how everything died. I mean, that's how I would imagine it if I was trying to like.
Oh wait, he says 1 atom per cubic centimeter, not 1 gram.
Of course, he says. So.
See, I guess that's the first lesson: is don't believe everything someone says in a comment section of the internet.
That's very true. So how exactly did the dinosaurs die? This meteor impacted in the Yucatan Peninsula of Mexico. So what were the events that transpired that allowed for this mass extinction?
So there are a couple of things that happened. When it actually hit, I mean, if you were living at the point of impact, that was a bad Tuesday 65 million years ago. So it actually does hit with an explosion. And this explosion actually blows out a shock wave and a fireball associated with it. So everything within a couple crater radiuses of the crater would have just been obliterated. So if you were living at the point of impact, you would have been hit with a shock, blown over by the wind, hit with a shock wave, then pummeled with sandblasted dust coming at you at, several tens of miles an hour or more. And so it would have been a bad day if you were living right there. But the really big thing, and what makes it a global mass extinction instead of just bad for the things that lived there, is it threw up dust and rock particles into the atmosphere that covered the Earth. You see effect of this. You see layers in Italy where it's the rain out of dust. This really was a global layer of dust covering the whole atmosphere. And what that does is it blocks the sunlight. And it cooled the planet. Ooh, wow, what was that? I hope everything is still there. The picture changed. Peter disappeared. But I'm just going to keep talking. So what happened is...
Sorry about that.
Looks like he's hit the wrong. So it cooled the planet. Lack of sunlight cooled the planet, which made it harder for things to survive. It also blocked out sunlight, which meant that the plants could not make sugar and photosynthesize anymore. So all the plants die. And that sort of ricochets up the food chain. Once all the plants die, then all of the things that eat the plants die, and all of the things that eat the plants die. And it becomes a bad day. And this is really why it affected the bigger things. It takes a lot of energy to sustain a giant dinosaur. If you're a small rodent, you don't need that much food. You can survive a little longer.
The cockroaches were doing just fine during this time.
Cockroaches. Okay, so Max will appreciate this. I'm convinced that dark matter is cockroaches. They're everywhere. You cannot destroy them, and they're there even when you can't see them. Dark matter.
Max says he does not appreciate this. Nate was calling in just now. Nate, if you can call back. I just wanted Steven to finish his question before I let you on cam there. So if you can call back in, or maybe he's having some Wi-Fi difficulties. Somebody also asks here on the side, have you recovered any non-Earth originated material from the ocean? Are we looking there, or are we just looking on land?
Yes, in a sense. So there's a group that goes down to Antarctica every year to look for meteorites there. And one of the places they go is along the edge of the ice. And these are areas where ocean currents sort of upwell and bring stuff from depth up onto the surface in these waves. So we get stuff sort of concentrated there because of the ocean currents. We're not going down onto the ocean floor to pick them up, but in a sense we're finding them near-ish or related to the water. But considering that there's significantly more area of the planet underwater than land, it's probably a good place to look.
Yeah.
Although you probably wouldn't want those as much because the water is going to change the chemistry of the meteorites. And one of the reasons that falls are so much more useful than finds is you want them as pristine as possible. So when you do your chemical analyses, you're looking at something that chemistry is reflecting outer space. water tends to alter the chemistry. So something that's been sitting in the ocean probably has chemistry that I would not trust as reflecting outer space.
So that's interesting. You want to understand something in its native environment, and Earth is not space. So this orbiter that just landed on the Philae comet, is that right? Yeah.
Philae?
How will that expand our knowledge of these rocks? Because now we're really testing it in that environment. Nate, I'm going to let you on cam.
Yeah.
Let's let Steve finish his answer to my question.
The Philae landing was, y'all have heard about this, but when they caught up with a comet. Oh, hello, Nate. I think it's just incredibly cool that a comet is moving really fast through the solar system, and we launched a spacecraft and basically caught up with and lassoed a comet. I mean, that's just really cool engineering. But what was really neat about that is we don't know that much about comets. And so anytime you land on a body out there that we have never studied before, everything you learn is going to be awesome and exciting. Because it's new.
That's social engineering.
I agree.
Every little thing that somebody says is social engineering.
Yep, we need engineers.
I've seen Nate before, so that was a great point. I'm going to go back to some of the questions on the side here. And Max was saying, slightly related to recent topics of discussion, physicist Lisa Randall recently wrote a book discussing whether dark matter causes mass extinctions.
I heard about this. Yeah, she was on. They interviewed her on Wait, Don't Tell Me this weekend, I think, which, if you don't watch Wait, Don't Tell Me, it is or listen to, it's not a TV, it's radio. They are hysterical and they're amazing. But yeah, she was interviewed. I was going to actually look up that book after hearing that show last week, because that was new to me. I didn't realize that there is a dark matter dinosaur connection. I'm just going to plug in my...
We don't want to lose you here.
Yeah. Has anyone read that? That was new to me. I thought it was really interesting. I'm curious what people would have to say about it.
I had briefly read an article about this, but I don't know much about it. So, but I believe it has something to do with how, as our solar system crosses a plane of dark matter, that it creates some sort of fluctuation that relates to mass extinctions. I think that's in very layman's terms that I could be completely wrong about. So, interesting. Let's see here. What else do we have here on the side? Oh, somebody asked, Joe Anderson asks, what's the most awesome thing for you found by New Horizons?
Ooh. Well, the giant mountains of pure water ice are pretty awesome. That was a surprise to a lot of people. I guess it was a surprise to me. I didn't really think about it enough beforehand for it to be a total surprise. But yeah, no, the mountains of water ice is particularly cool.
I mean, we saw a lot. I mean, there was a lot that we didn't know about Pluto when that satellite passed by. I mean, did we even know that there were mountain ranges on Pluto to begin with?
No, we didn't know there were mountains.
We just knew that it was like a pixelated, image in the distant solar system, right? Yeah. That's crazy. So I think, and anyone feel free to answer questions, keep asking questions, whatever topic, and you're more than welcome to jump on cam here too if you want to ask Steven a more direct question. But I really want to understand your passion for science. What is it that got you interested in science, and where do you think, when you think of science today, what do you think of the current status of science?
Ooh, that's an interesting question. So I guess the first part was what is my interest?
Yeah, how did you get interested in science in the first place? And yeah, we'll start there.
So I got interested in science because when I was in high school, and actually a little bit before high school, the county I grew up in, as part of the K through 12 school system, had a science center, that was basically funded as a school, but it was all master's and PhD scientists who teach science for the school system. They did outreach or field trips, and they had a planetarium and an observatory, a 64-acre hardwood forest that they taught all like summer programs. And in high school, you could take your science class, you could apply to the special program and take your science half a day at the science center, not reading out of a textbook, but going out and learning about trees by measuring and counting trees in the forest, or going up to the observatory and looking at double stars and calculating their distances from each other. It was basically a real-life hands-on science, not reading stuff out of a book, which is useful, but not the same as actually having the hands-on experience. So after doing those programs, I got involved working as a volunteer there, and just sort of being around that, having the, scientists are a fun group of people to be around, and it's just really exciting and energizing to just be a part of that where you're doing real things. And it's also neat to have that experience at a young age. I mean, I feel very lucky. Most people didn't get to use an electron microscope when they were in 9th grade. But I think it's great, and everyone should get that opportunity at some point, to start young and capture people before we lose them to other things.
Joe Anderson asks, are there any big questions that you are personally hoping to answer in your work?
Before I answer that, someone asked a question about my mic. Can y'all still actually hear me?
I can hear you. I don't know if... I think... yes, people can hear you.
Okay. So what was the question?
He is asking, are there any big questions that you are personally hoping to answer in your work?
Ooh, that's hard. Big question.
What keeps you up?
Yeah, I don't know. So personally, maybe this is just my nature of liking just being a regular lab scientist and field scientist. I actually get really excited by the details and piecing things together. The big questions, of course, are always interesting. But to me, even the little things, to me, I get really excited by the little details. But I'm trying to think of a big question. Well, okay, so one of the things that I'm really interested to find out would be, what was the early solar system like? When you go back to the first 100 million years of the solar system, what was that like? What was, how many large planets were slamming into each other? What was happening? How do you actually go from cloud of dust to stars and planets? What was that like? What did that look like? How do you do that?
How do you do that?
Is that big enough for you?
I like how you stated that. How do you do that? That's pretty good. I could be entirely wrong about this, but it was a big question on how planets formed, how stars form, how matter coalesces. Weren't they in the space station and someone just kind of released some cereal or sugar into zero gravity, and they noticed that everything started kind of clumping with each other?
Yeah, zero gravity is really weird. There was a really fun video that we used to use in teaching for 5th grade science camp, where a bunch of astronauts took everyday objects, mostly toys, up into the space station and tried to play with them. And it's just so mind-boggling, the things you don't think about. The one that sticks out in my mind is playing jacks, those things that you toss with the ball. Try doing that in outer space. There's no gravity, you can't bounce the ball. The jacks just float, and it's like not a big deal to pick them all up in one swing. Yeah, it's always counterintuitive, the things that happen in outer space. Particularly liquids do really weird things. They form these weird balls of liquid that just hang out.
Yeah, I mean,
it's totally not answering your question.
But I mean, it's true, right? Matter adapts its the state that it is most favorable for, given the environment that it's in, right? So in zero gravity, water is going to form like a ball, where on land, on Earth, water is flat, right? You can pour water on the ground and it doesn't form a ball.
Yeah, but the balls of water floating around the space station is really bizarre.
We got 2 minutes left, and I just want to ask, what do you think? What is your thoughts on the current status of science? Is is today an exciting time to be a scientist? And more importantly, we have fewer scientists in the room than we'd have people who are science enthusiasts. So is today the best time ever in human history to be passionate about science?
Oh, I think so. I mean, you have the added benefit of it's not during the time of Galileo, and they're not burning scientists. But aside from that, I think it's actually a really good time. I'm really excited, particularly about a lot of the science in social media stuff that's happening. I mean, the IFL Science website. I mean, there's just so much energy and enthusiasm, and people really like science, and that's incredible and awesome because we need people going into this. And, you know, I'm a big of the opinion that you need excitement, and, you know, science is exciting. We're doing really cool things, and showing people that, getting people excited so that we can keep doing it, I think is really important.
Absolutely. Well said. And I just want to plug one more time, since we got 1 minute left, that we are doing this. We are based out of the Alan Alda Center for Communicating Science at Stony Brook University. Steven and I are avid science communicators in our community. We go to local high schools and libraries, and you know, this is what we love to do. And we hope to have Science Unplugged be a routine show, and we can get scientists from all different areas of science to share their experiences with us, share their insights, their questions, and more importantly, we need all the people that are viewing today to participate. And we want really what drives us is the questions that you guys are asking, because you know, we're asking the questions too, but we can only, you know, our brains have only so much power, right? And it's really the questions from the people that don't have expertise in the field that are really the best questions, right? I always like to approach science from a naive position. And when you're too focused and you know too much about something, you kind of get tunnel visioned, right? So my goal from this is to actually make the viewer feel like they are the scientist, you know, and maybe kind of live vicariously through us a little bit.
Yeah, no, definitely.
So
thanks everyone for tuning in.
Thank you, everybody. And we're going to stop the recording here.